Hi, welcome to lesson 15.3, where we're going to use double integration to calculate area. Now, you might think this is a step backwards because in 15.2 we calculated volume using double integration, but I want you to see how flexible this idea is. Oops, there we go. All right, new software. Since we had the upgrade with Mac OS Catalina, my other presentation software doesn't work. So I've got this website that's doing a pretty good job. All right, so here's the main idea. There's two ideas in this section. Here's the primary one. This double integral formula over here, the double integral over the region R of f of x, y, dA, calculates volume under a surface, F, okay? And it's over a certain region R in the xy plane, a flat region, and that gets partitioned. And you remember the definition where the partitions delta x by delta y get smaller and smaller and smaller. We take the limit as those partitions reduce down to an area of 0, and that gets our exact volume between a surface and the xy plane. So or a region of the xy plane R. And so if we just take our function f of xy to always be 1, which is just a plane, z equals 1, a flat plane with a height of 1, or excuse me, the area under that plane would be a height of 1, so that we're only calculating dx dy over the region R. That would give us just area. So that's a really handy way. Notice there is no function in here, so you could put a 1. If f of xy is 1, you could put a 1 here if that helps you remember that. But this will give you just the area of the region R that is underneath that plane at z equals 1. So that's the main idea in this section. This is a pretty short section, by the way. So here we go. Let's take a look at example 1. Now, what I want you to realize is that in a question like this, I would not be providing the sketch over here for you. I did this for convenience in our video lesson so that you can see a nice clean drawing rather than my attempt at drawing on an electronic tablet. But you would be expected to provide the sketch in your work for problems like this on quizzes and tests. You would start, not having seen this picture, find the area of the region R bounded by y equals x and y equals x squared in the first quadrant. So you would need to draw these two curves in the first quadrant, determine what their points of intersection are so that you could figure out your integration. Now, they did not specify, we have to do this, right? Essentially. And they did not specify an order of integration. They often default to dy dx, but that is totally and completely up to you. If the order of integration is easier to integrate, or the problem is easier to integrate, if you reverse the order of integration, that is totally your choice. And sometimes if you set one up and it turns out to be ugly, you might want to try switching them. So in this case, they've drawn both our arrows for us here. I don't think it really matters. They've chosen to do dy first by how they've drawn this, is what I can tell. But you would not be looking at these red arrows. You would be choosing. So I would draw an arrow up, and then I would draw an arrow across, and I would decide which one I want to do first. No matter where I draw this horizontal arrow from the bottom to the top, I cross first the line and then the parabola. So this would be completely fine to do dx dy. The way they drew it, dy dx, everywhere from 0 to 1, this arrow hits first the parabola and then the line, so you'd be perfectly free to do dy dx. So, I don't know, which one did I choose in my notes? I did dy dx probably out of habit. Okay. So I think they did dx dy in the book, so you'll be able to see it the other way here. Now I have to do the limit. So with respect to y, vertical first, I'm going to hit y equals x squared first, and then when I exit, I'm going to hit y equals x. So this may feel funny. You may consider x squared to be larger than x, but remember we're dealing with values from 0 to 1. So x squared is always going to be below x in the first area square of the first quadrant. All right, now the outside limits have to be constants, so we just need the lowest x value and the highest x value along this horizontal red arrow. The lowest is 0, the highest is 1. So those are our limits there. All right, just to refresh you on the integration part, this is a very simple integral, happily. The integral with respect to dy would just be y. Okay, so you could put in this step if you care to. All right, if you wanted to skip that step and go straight to this, I would be fine with that as long as you don't get it wrong. Okay. Please don't skip too many steps because that's when people start messing up, even on easier problems. Their brain gets ahead of their pencil. So if you skip any steps and your work is wrong, it's very hard to get partial credit, so watch out for that. All right, so now integrating with respect to y, I'm going to have 1/2 x squared minus 1/3 x cubed using the power rule, and that's going to be from 0 to 1. Nice easy limits. Substituting in 1, I'll get 1/2 minus 1/3. Substituting in 0 will be minus 0 for a polynomial function. So this is 3/6 minus 2/6, or an area of 1/6 in the xy plane. All right, so that's the basic concept in this section. Let's take a look at how this could get more complicated. I'm going to pause for a second because my slides are messed up. Okay, slides fixed. All right, on to example 2. So this is an example of how the order of integration is better one way than another. So in this example, first we choose to do it this way. Okay, so let's say you have your region. So find the area of the region R enclosed by the parabola y equals x squared and the line y equals x plus 2. Now this is not all that different from the last one. The line here has been moved up 2 units, but notice what has happened. We now have a region, and you wouldn't know that this would be split into 2 regions yet. You would have sketched this, you would have been looking at it kind of like this here, and I have to train you to recognize when you can't do it all in one integral. So if you choose to go horizontal first here, so with respect to x first, you draw a horizontal line down here. Notice we don't hit the line y equals x plus 2 at all here. And up here we do manage to hit both curves. So it's fine from negative, or from 1 up to 4. But down here from 0 to 1 on the y-axis, this is not going to catch the bottom part. So if we wanted to do it this way, if we had to do it in 2 pieces, R1, okay, if we do it with respect to x first, so we're going to do dx, dy, the line, the horizontal line, is going to hit the left side of the parabola as it enters region 1 and hit the boundary of the other side of the parabola in the first quadrant as it exits the region. So we have to think about here, x is actually equal to plus or minus the square root of y. And it's going to hit the negative side going in and the positive side going out. So we would have to do this. And when we integrate with respect to x first, we often forget that this can't be left as y equals. So I think that's why they tend to default to dy dx, because we tend to have functions of x expressed as y equals in a form that's useful to just jump in with. But if you're going to integrate with respect to x first, you're going to have to solve the equations for x. All right, now for the y part, that's just the constants. The bottom of this region is 0, the top of this region is at 1. This horizontal line divides the regions. So that would be region 1, and then we would have to add in region 2. Okay, so that would be equal to, if we were still insisting on doing dx dy here, we would hit the line first and then we would hit the parabola. So from x plus 2, that's to the left in the x direction, and to the right would be the greater function. X equals the square root of y, the positive side. So, excuse me, this would be, this has to be x equals, right? So I have to listen to my own advice here. This would be x equals y minus 2. So I don't like it when it does that. I don't know why it deletes the whole slide behind there. So we're going to scratch this out and just say y minus 2. There we go. And then in the y direction, we start at 1 and go up to 4 for region 2. So we would have to calculate two different integrals and add them together, and that would give us a fine answer. But if you don't want to do that much work, if you'd like to simply do this once and be done with it, we can calculate our area with respect. Notice that we can judge this without having to know ahead of time by trying first horizontal and then trying first vertical and seeing which one will give us what we need. And what we need to recognize in order to judge between them is there anywhere from here to here, from x is -1 to x is 2, where drawing a vertical line does not hit first one function and then the other in the same order. And you could draw it way over here, you could draw it way over here, but any vertical line drawn upward is going to hit first the parabola and then the line, no matter where you draw it from -1 to 2. So this one I know can be done in one calculation and not split into two regions. So if I do dy dx, that will get it all in one. So learning to recognize that is huge. Here, horizontal did not hit both functions, whereas here horizontal did, and that meant that I would have to have two regions. If we go from the parabola, and since we're with respect to y first, these are in the proper form to go ahead and use. And we're going to hit the parabola on the way in and hit the line on the way out. So we're going to do x squared up to x plus 2. All right, and then the y, the constant values of y, -1 over to 2, that would give us in the horizontal direction. And now we can just calculate this, okay? So I'm going to show you that shortcut again. I could just put evaluate y from x squared to x plus 2, knowing that I'm going to take the top one and subtract the bottom one, or I could just do this. All right. So to slow down and repeat myself there's a step here you don't have to show, and it would be this. The integral of 1 dy is just y, and that would be evaluated from x squared up to x plus 2, and then I would substitute this in and subtract substituting this in. So I would wind up with this. So I find this step, don't forget that, to be unneeded, unless you just like it and want it, and that's absolutely fine. Okay. So integrating with respect to x, we're going to end up with 1/2 x plus 2x and minus 1/3 x cubed. You're going to get really good at the power rule if you're not already. All right, now we don't have any zero limits, so we got to do some substituting in here. Don't like to get my lines mixed up. Okay, so that's going to be equal to, subbing in 2 times 1/2. Actually, this would be squared right here, I believe. So 2 squared is 4 times 1/2 is 2. And then 2 times 2 would be plus 4. And 2 to the third power is 8 over 3. Okay. And then substituting in -1 squared is +1 times 1/2. -1 times 2 is -2. -1 cubed is -1 times -1/3 is +1/3. All right, so we've got 6, which is 18/3 minus 8/3, that's 10/3. And 1/2, that's 3/6, and 2/6 is 5/6. Minus 12/6 would be -7/6. So we need 6, so 26 plus 7/6, 27/6, or 9/2. All right, and there we go. So moving on. All right, so here's the other concept using the one we just learned, the average value. Now you did this in single variable calculus as well, but if we want the average value of a function over a certain region, we actually are going to include our function here in the integration, and then we're going to divide it by its own area. So this would be the volume under the surface divided by its area, and it gives you the average height of the function above the xy plane. So that's why this gives you the average value. But we want to understand what this means in terms of applications. So if F is the temperature of an infinitesimally thin plate over R, that's a typo right there, then the average value formula up here gives the plate's average temperature. Okay, that makes sense. If F is a population function, then it gives population density. And if f of xy is a distance from the point xy to a fixed point p, so basically a distance formula function, and that point P is in R, then the average value formula gives you the average distance of points in that region from that point P. So that might be in a statistics setting, that sort of thing. But there's plenty of applications. Those are just the ones that you're likely to see here. So let's look at one last example. So they were kind and gave us constant limits of integration, but let's just do this one together to get some good practice. Find the average value of f of xy equals x cosine xy over this rectangle. So average value, so 1 over the area of R. Okay, so R's area. I don't know if that's a appropriate abbreviation, but that's what I'm going to do. Of x cosine xy. I see a substitution in my future. And if I substitute in, I'm going to do with respect to y and then with respect to x, because I can do a substitution for y here. Okay. And then we have to do with respect to y first would be 0 to 1. With respect to x would be 0 to pi. And so I saw this rather quickly. Most people, if you're not in practice on it, you may not see it very quickly. But if I want to do a substitution, u is xy, and I'm evaluating with respect to y, then du would be x dy. And so substituting that in, and I will go back and get, this area is just the area of this rectangle. So this is pi, if we're thinking about this, 0 to pi and 0 to 1, then this rectangle is the area we're integrating over, would just be a rectangle that's pi by 1 units, or an area of pi. So I'm going to go ahead and do 1 over pi here. And we'll do the inside integration. If I do a u substitution, it's proper to go and change the limits. So if u is what I'm integrating with respect to, I can substitute in 0, y is what I'm integrating with respect to, 0. The bottom limit for y would be 0, so the bottom limit here is x times 0. And plugging in y as 1 over here, I get the upper limit is x. And now I can do x dy is here, so that's going to give me my du. And this is going to be cosine of u. So there's cosine of u du, and that's the inside integration, and I just have to bring my dx down. Okay. So I'm focusing on this integration. And I did my u substitution so I could calculate that integral. Okay. So just bringing the rest along for the ride. I'm going to have the integral of cosine of u is sine of u. And we have to integrate that from 0 to x dx. So we're going to have 1 over pi, 0 to pi, of sine of x minus sine of 0. Well, sine of 0 is 0, so I don't have to worry about that. Putting in my differential. All right, second integration. The integral of sine is negative cosine x, and we're going to evaluate that from 0 to pi. If this confuses you that that's curved and not bent, that's exactly how I was taught it, and I've tried to switch to what your book does now, but not always with so much success. Just old habits die hard. All right, 1 over, 1 over pi. I don't like that. Too high. 1 over pi times. All right, so we're going to have negative cosine of pi minus negative cosine of 0. 0, not theta. So we've got 1 over, if I could do that right, this would be nice. 1 over pi times, cosine of pi is negative 1 times negative is 1, plus cosine of 0 is 1, so we've got 2 times pi, 1 over pi, which is 2 over pi. So the average value of this function over this rectangle is 2 divided by pi. All right, that's what I've got for you this lesson. Thanks for listening.